Uh, Hello, everybody. Welcome to the third lecture of Andreas. If you have missed the first two or you have listened but you want to listen again, they are available on YouTube, and the link to YouTube is on the field's website. Please go there and watch again if you wish, or watch if you have been absent. So, Andreas, please, with the third lecture.
Okay, thanks a lot for the introduction and for giving me the opportunity to talk about all this stuff. So the third lecture will be, as I announced earlier, on a specific technique to solve interpolation problems. And it will be the D-bar method. Well, D-bar methods, they can be used in different contexts. And I would like to show you a specific situation in connection with interpolation. And the setting I've chosen is the setting of Fock spaces. I could also have chosen Bergman spaces. There's a kind of meta theorem which tells you that if you are able to prove something in the Fock space, then you should be able to do it in the Bergman space and vice versa. Maybe that's not always true, but often it's true, and the techniques are quite close. And then you have to replace the underlying metric, which is Euclidean in the Fock space, and sort of hyperbolic in the Bergman space. So to make things easier, we do it in the Fock space. So what is a Fock space? Well, we saw definitions yesterday in the last two talks. So Fock space, you can define it in a quite general setting. So if you pick phi, a subharmonic function on C, then you can introduce this weight here. So e to the minus phi z. And then we want this integral to converge against this weighted Lebesgue measure. Of course, you could also consider other p's, but again, I will stay in the inversion situation. Though probably for the bar techniques, this is not very relevant. So again, also as I said, the n here is planar Lebesgue measure. And so this problem was considered in the classical Fock space by Seib and Waldstein, who characterized interpolation and sampling sequences for the space when phi z is z to the square. So then you have a Gaussian measure here. Then there were several generalizations to more general phi. I mentioned Ljubaski and Seib. And also, in particular, Berndsen and Ortega-Cerda. In particular, I mentioned this paper because I want to give you the proof which was given in this paper by Berndsen and Ortega-Cerda in the easy situation when phi z is z squared, because then the computations are quite clear, transparent. But in fact, they generalize to the more general situation. There's also a paper by Nicolas Marco, Shadi Massaneda, and Kim Ortega-Cerda in 2003, where they consider a quite general situation. And well, this is a very nice paper. It contains many, many tools that you can use in other contexts. There's a preprint by Orsoni and Conete on sampling constants using tools which have been developed there. Okay, more recently, well, okay, this preprint I was just talking about is very recent. But I would like also to mention this recent activity in so-called small Fock spaces. Small Fock spaces means phi grows slowly. If phi grows slowly, it means e to the minus phi decreases slowly, and so the functions f cannot be too big. And of course, this weight phi should not grow too slowly, because otherwise this by Liouville's theorem, the space will be just constant. Well, it will be empty, zero. But if phi grows sufficiently slowly, then we call these spaces small Fock spaces, and there were different developments. Here's a paper by Belov, Mengistier, and Seib from 2011. They make some developments related to discrete Hilbert transforms, allowing to discuss the interpolation and sampling problem in this connection. It should also be mentioned that for these small Fock spaces, in fact, you can identify these spaces with the branch spaces. For specific small phi of the logarithm to some power, Borchev and Liubarski, they exhibited reference re-spaces. So it was mentioned yesterday, I think in Martin's talk, that in Fock spaces, there are no re-spaces because there's some contradiction between this interpolation and sampling. I will discuss this in a minute. But if the weight phi is small enough, then re-spaces appear. And so Borchev and Liubarski, they were able to identify re-spaces in this setting. So yesterday, Martin Bonik, he asked the question, does re-spaces exist in Paley-Wiener spaces for arbitrary bounded measurable sets? So in these Fock spaces with small phi, this is possible. And we were working on this problem with Baranov, Guimont, and Karim Kelly. And starting from this result by Borchev and Liubarski, we were able to give a perturbation result. So if you perturbate this reference re-spaces from the paper by Liubarski and Borchev, then if you perturbate in the right manner, then you still get re-spaces, and this is kind of optimal. It's in the spirit of this Ingham-Kadetz theorem that I mentioned in the very first lecture. Okay, this is some history for these spaces. Here is more. I recall Seib's paper from '92, which is a very important paper, as also mentioned yesterday by Charlie Groschinik, who characterized interpolating and sampling sequences in the Bergman space using densities. Densities, well, they might appear somehow difficult to compute, but normally you should be able to compute them because you are counting points and you relate the number of points to area and so on. So this should be possible. These are geometric characterizations. And well, yesterday the question was asked about interpolation in Hardy spaces in higher dimension. I was mentioning, well, for checkable conditions, I think the situation is difficult. Okay, I mentioned also that the Carlson condition I discussed yesterday, and I mentioned from the very first talk on, so this infimum of B lambda and lambda n, this is an extremal function characterization. I also mentioned that this is equivalent to have uniform minimality. In fact, it turns out that a similar characterization exists also in the Bergman space, and this is due to Schuster and Seib. I commented on this yesterday at the end. In fact, this extreme function characterization is again connected with uniform minimality. But this is an uncheckable condition because it's very difficult to get a hand on these extreme functions. I also mentioned that there are many results in the Dirichlet space, and a strange thing is that there are some unpublished papers. Okay, so we have this result by Allman, Hartz, McCarthy, and Trichter, who give this result, which says that in certain spaces separation in Carlson measure condition imply interpolation. Okay, this was just to complete some history on this interpolation and sampling problems. Okay, so let's get back to a concrete situation, and I think the aim of these courses is also to introduce to known techniques, maybe PhD students or want to know a little bit about interpolation and sampling. So as I said, I will consider this problem in the Fock space, and now I take very specific situation, and I apologize that my normalization is not exactly the one which was chosen yesterday in Charlie's talk. He put a pi here, but I take 1 here. Okay, so this is the Fock space of entire functions. The space is of course not reduced to 0. You have polynomials in the space because the weight is big enough. This space is a reproducing kernel Hilbert space, and I have a reproducing kernel. I mentioned this already in the first talk, and once you have the reproducing kernel, you can of course compute its norm. And in the Fock space, there's a natural density condition which appears, and it's defined this way. So you can define the quantities n plus and n minus, and it's just counting the number of points that you have in a disk, in a Euclidean disk D of radius r, okay? And then while you walk with your disk around the complex plane, and each time you will count the number of points that you meet, and you will take the biggest number or the soup of the number of points that you can meet. This is n plus, and similarly you will call n minus the minimal number of points that you can meet when you walk with your disk of radius r through the plane. Of course, n minus could be 0. Okay, this is a possibility. And then we can define densities. So, of course, if you increase the value of the disk, then you need more points. This should be somehow comparable to r squared, because if you double the radius, then you quadruple the area. And so that's exactly what we do. We count the number of points and we divide by the area of this disk. Okay, of course, if I give you an arbitrary sequence, it can be complicated to compute these numbers, but if your sequence are more regular, then you can get some results. Okay, and D plus will be the limit soup of these mean number of points, and D minus will be the limit inf of these mean number of points. The fact of choosing here disks is not very important. Landau I think it follows from Landau works that you can replace this by other compact sets. Okay, so I have given the definition of interpolating sequences. So interpolating sequences are sequences for which the restriction operator, so R is the restriction operator. So I consider the trace of the function in the space restricted to lambda, and it should be in this weighted L2 space. Here it's again 1 over the norm of the kernel squared. And for sampling sequences, well, there are different ways of expressing it. Well, it's essentially having this double inequality, which was mentioned also yesterday in the talks in the afternoon. Another way of saying it, this is that the restriction operator is isomorphic onto its range. Okay, we have also definition of uniformly discrete or uniformly separated, which means that the now Euclidean distance of 2 points is bounded from below by some constant. Okay, yesterday in the Hardy space, the metric we had in mind was the pseudo-hyperbolic metric. And today it will just be Euclidean metric. Okay, we have two theorems, which go back to work by Seip and Wallstein. The first one is lambda is a sampling sequence if lambda is a finite union of separated sets, and at least one of these separated sets which compose lambda satisfies this lower density condition. Okay, lower density means in the sense that if R is big enough, okay, then all the disks with this radius will meet the least number of points. So I was saying n minus could be 0, but for sampling, this case cannot happen. You have to have in a disk, if its radius is big enough, then for this radius, if we run through the plane, it has to meet the least number of points. And this is reasonable because if you want to sample, it means that you can recover the function from its samples, from its discrete values. So you have to have many points. And so if you don't have enough points in these disks, then, well, the function you cannot reconstruct it. Similarly, for interpolation, the characterization is the sequence should be separated, and the argument to be separated is a little bit like the arguments that I have given before in the Hardy space. Again, you interpolate the weighted one in one point and zeros in the other points, and then you can use separation. Okay, you cannot get in a very small time from the value 1 to the value 0. That's the idea. If you want to do this, your function has to be big energy, and it has to have a norm which is exploding. Okay, and moreover, your density, your upper density should be bounded now from above. Of course, to interpolate, if you have too many points, then you have too many oscillations and you have no hope to interpolate. So your upper density has to be bounded from above. And interesting consequence, which was already mentioned yesterday in the talks, is from these two conditions, you can conclude that in the usual classical Fock space, there are no simultaneous interpolating and sampling sequences, which I called also complete interpolating sequences. Okay. So previously, and this was my first slide from the first day, Lagrange interpolation is you construct a function vanishing in all the interpolation nodes, if you have finitely many, and it's 1 in 1 point. And from this, you can construct interpolating functions easily for polynomials. If you go to the infinity case, okay, then the situation gets more difficult, but still you can use this idea, constructing a function vanishing in all the points except 1. And this, in fact, constructing a B orthogonal sequence to normalize reproducing terms. Okay, this was an idea which was used several times, and this idea you can use also in, for example, in the Peggy-Wiener space, in certain different spaces of entire functions, or in the Fock space. Here we will try to use another road, and we want to use the bar methods. And in particular, I will use the method which is presented in the Berndsen-Ortega-Cerda paper, but I will just apply it to this very simple case where the weight is e to the minus z squared. So the subharmonic function phi is mod z squared. I mentioned that there is a D-bar proof by Amar for interpolation in H infinity. I don't remember exactly which year it was. Okay, so in fact, we want to try to show the sufficient condition, the sufficient part of the Seip-Wallstein result using this method. Okay, so here we go. The main idea is to construct first a smooth interpolating function. And this is easy. But then once you have constructed the smooth interpolating function, you have to do two things. You have to correct this function in order to make it analytic. And so in order to make it analytic, so you have to ensure that the correction you will add to make it analytic stays in the right space. And also you shouldn't destroy the interpolation. Okay, this is the main idea of what I will explain now. So our assumption is the sequence is separated. Let's say delta is a separation constant, strictly positive. I should have made this precise here. And the upper density is controlled by 1 over pi. This means, again, so D plus is a limit sup, okay, over R. And if the limit sup over R is strictly less than 1 over pi, then I know that for an R big enough, this number of points, well, I could have said n plus. Maybe I should have put n plus here. Okay. Okay, there's a plus missing here. Of course, n is then also satisfying this condition, but okay, I could have said it's true for every z, so I don't need to put the n plus. Okay, no, I can, okay, excuse me, I'm confused. So this is for every z. Okay, so first step is computing the smooth interpolating function. And for this, I will start exploring this separation condition. And for this, I will introduce this function chi, which is a smooth radial cutoff function. So it's 1 in the neighborhood of 0, and it's 0 outside delta over 2. Okay, and so now I take all my points of the sequence, and I have drawn these gray disks, disks of radius delta over 4, and the bigger disks are of radius delta over 2. So chi is 1 in the gray region, it's 0 outside, okay? So here, chi is 1. Inside this gray disk, and outside here the function is 0, okay, everywhere. Okay, well, in fact, if I take a specific chi, I'm maybe a little bit too fast in my explanations, and so in fact, if I take the function f0, so I take now chi, I will translate it, and the chi z minus lambda n, so this will be 1 inside, so it's this function, okay, which is 1 inside the gray disk and 0 outside. Okay, so well, chi has been fixed once and for all, and it's smooth, and then the derivative, I mean the derivatives of this function are uniformly bounded. Okay, there's no problem here. And okay, the gradient of this function is supported on this annulus, because inside the gray disk, chi doesn't vary. Okay, so the derivative is 0, and outside also. So the support of delta chi is only on the annuli. And a naive approach would now be to set f0 to be the function sum vn chi z minus lambda n. So this chi minus z of z minus lambda n, okay, it's a little bit like this Lagrange polynomial. It's 1 in the point lambda n, it's 0 in all the other points. But of course, chi is not very analytic. All right, so let's move on. I recall that my function f0, oh, I should remove all the stuff here. So phi was a smooth interpolating function supported on d0 and delta over 2. It was 1 in the smaller disk inside. And I've set f0 equal to this function. And clearly, f0 in lambda k is vk. So I've used here the separation condition. Okay, so the sum, in fact, is okay. It's written here. So by separation, the sum is reduced to only one term for each z. If I compute in lambda k, so I've only the term in lambda k, so I get vk. This is no problem. So I have interpolation. But of course, my first requirement would be that f0 should be integrable with respect to this rate. So that's my requirement for f. And now this is not true for f0. Okay, if I take f0, then well, f0 takes this value Vn, which is more or less like e to the minus lambda n squared. Okay, it's not exactly e to the minus lambda n squared, but well, I could be in a very specific situation. Vn could be the sequence which is exactly equal to e to the minus lambda n squared and 0 everywhere. And it has norm 1, okay, in the L2 space. So my interpolating function should have a controlled norm. But now if I integrate against this way, well, this term is unfortunately not bounded in this disk. Okay, I will try to draw some picture here. So maybe if your disk is like this, V lambda n is like this. Well, if you are, let's say, inside the disk here, okay, then the e minus, well, it's e to the lambda n squared, the value of Vn. But inside the disk, the e minus z squared is much smaller. Okay, well, it's not, well, it's bigger than this expression. Okay, we should do the computation. As we know that e to the x squared over e to the minus ex squared over e to the y squared is not bounded if x minus y is bounded by 1, for example. Okay, you get e to the some linear term. So this explodes. So this is not exactly the right way to construct the smooth interpolating function. So we have to work a little bit more in this first step. And this is a little intermezzo, which I will do now. The idea is that you write z squared as lambda n squared. So if you can do this, okay, in a sense, the z squared, which is here, these will compensate. But let's look about the remaining part. In fact, this z squared, you can write it actually as lambda n squared plus a harmonic function and a bounded function, uniformly bounded function. And in the specific situation when the subharmonic function is z squared, everything is explicit. That's why this is quite easy to do. And okay, this is a direct computation. You can choose Hn to be this function, and we all agree that it's harmonic. Okay, it's a real part of the holomorphic function. And what's remaining is this Rn, which is z minus lambda n squared. And this has the nice behavior that it's bounded in the disk. It's bounded by delta over 2 to the square. All right, so how do we apply this? Well, since Hn is harmonic, it's the real part of the holomorphic function. Well, the holomorphic function is explicit here. Again, this is a very specific situation where I apply a general result from this Bernsen-Ortega-Cerda paper, where they do this for phi, for subharmonic functions. So you can run this argument more generally, but then of course this holomorphic function is not as explicit as here. Okay, so The idea now is to replace Vn in F0. We had Vn here, and instead of picking Vn, I will choose Gn, which is Vn e to the Hn over 2. So Hn is essentially this function. And if you compute this function in lambda n, well, it's 0. Okay, so this exponential will be 0. Okay, so Gn is Vn in lambda n. So I can put the Gn here. And again, this interpolates as it should. So the introduction of this additional factor e to the Hn over 2, will this save our situation? And yes, it will. Now, if I'm in a neighborhood of the disk, so again, since chi vanishes outside these disks, it's enough to consider what happens inside the disk. So here I compute the function I have to integrate. And now I replace, as I should. So f, well, inside the disk, it's just Gn. So I have to compute the modulus of Gn, and the modulus of Gn is the modulus of Vn e to the real part of Hn. Okay, maybe I have lost an over 2 here. No, it's okay, because I have the square here. Okay, and then this expression, I can rewrite it using this. And I get Vn squared e to the minus lambda n squared. And then here's some bounded expression. So all this is bounded by Vn squared e to the minus lambda n squared. And now by construction, this is summable because my trace is in this sequence space. Okay, so this is not the principal part of the d-bar method. It's just there's some complication because the weight is exponential with z squared, and so we have to adapt a little bit this function. In other situations, this is not required. Okay, so let's move on. F is this function. It interpolates as it should, and so if I integrate this function, I get this sum of all these disks, and by the computation we just obtained, so we get this chain of inequalities, and at the end of the day, okay, this is just the area of this disk. Okay, maybe this should have been Z. Okay, this is a disk centered at Z. No, at lambda n, excuse me, I'm confused. Okay, and well, this sum is of course bounded by hypothesis. Okay. So buff reasoning, as I already mentioned, applies to more general settings, and that's the paper of Bo Berndson and Kim. The function f is holomorphic in the small disks. It interpolates and it satisfies the right integrability condition. And now we have to modify f to make it holomorphic, but keeping the interpolation condition and the integrability condition. Okay, and that's the next step I would like to explain. And for this, we will use the bar method. Okay, again, f is this function. Gn is holomorphic in a small disk. Gn takes the right values, is smooth interpolating, and I recall that, well, in fact, it's correctly, yeah. It's not this function which is supported in this. It's this function, okay, which is supported in this annulus. Okay, the function chi of z minus lambda n, the gradient is supported in the annulus. Okay, so we compute the d bar of the function f, of the interpolating function, okay? And the d bar, well, it's supported, well, Gn is holomorphic, okay? And so it doesn't feel the d bar, and so the d bar is only felt by this function chi. Okay, and then I have to look if this W is in the right space, if it also satisfies the integrability condition. And the argument is essentially the same that I gave before for the function f itself. Okay, so the d bar of this function is in the right space. This is nice. Okay, so W is the d bar of this function. And now, so what we will do is we will solve a d bar problem. So we will take the given function W, and we are looking for a function U such that d bar U is equal to W. So we solve a partial differential equation. So, well, it's essentially something related to Cauchy-Riemann. Well, at the end, my resulting function will satisfy the Cauchy-Riemann equations. Okay, I give, of course, if you want to solve this problem, then of course you would like to know in which space you solve it. And so we have some liberty here, and Hartmann's theorem, which says that such a solution exists, he claims that, well, you can do this in a quiet channel setting for a subharmonic function phi. So if your right-hand side is in the space, then you will get a solution more or less in the same space. So we have, unfortunately, here some additional weight appearing that we have to take into account. Okay, but suppose this is possible, then if I set f to be big F minus u, then I compute d bar of this is d bar of this little f is d bar of the big F minus d bar u. D bar of big F is w, and w minus d bar u is 0, because that's what we solved here. So this means f is holomorphic. So we came from a smooth interpolating function to go to the holomorphic function. The next step is we have to choose. We cannot choose phi to be just z squared, because phi z squared, well, this is no problem, but well, it will destroy the interpolation condition. Okay, so we have to choose phi in a convenient way. So first condition is phi z has to be bound by z squared, because then this expression is bounded by this expression, and so my function f will be in the space. Okay, if we have this inequality, and then we get this inequality, and this means the u that we will add as the correction term, well, it's also in the, it satisfies the right integrability condition, and so the little f will satisfy the right integrability condition, and so f will be in the Fock space because it's holomorphic. The other condition, which is a little bit more intricate, is that, in fact, phi, when I'm close to a point, an interpolation point, so where I interpolate, then, in fact, my phi should be in such a way that this gets very big. In fact, this should have a pole. If this has a pole, then necessary w, which is a holomorphic, no, it's not a holomorphic function, but it's continuous, in fact. Then this function has to be 0. Okay, it's not possible that to integrate this pole against some holomorphic function. So the idea is to do this. Okay, and ideally the Laplacian of phi should be bounded from below by a strict constant, because then I don't need to care about this. Okay, so I have to look for a function phi satisfying these conditions. Okay, how do we do that? Now I have to consider the density, of course, and I recall that the density told us that the number of points in a disk with radius r is controlled by qr squared, and q is strictly less than 1. Now, in fact, my phi, I will add this weight, v, and v is more or less the Taylor expansion, Taylor development, the Taylor series to the order 1 for the logarithm. Okay, so if I take the logarithm, I subtract essentially the first order Taylor expansion. Okay, and so I've drawn the graph of the function log x plus 1 minus x. So this is negative. Okay, so this means phi z is less than z squared, and so we get this condition for free. Okay, and what should I to say? Okay, so we also observe that this function log x plus 1 minus x, well, it goes smoothly to 0 at 1. This is an important observation, because this means that the Laplacian of v will not have any weight here. Okay, at some point we have to compute the subharmonicity of phi, and so we have to compute the Laplacian of phi, and we know the Laplacian of z squared, this is 1 essentially. And then we have to compute the Laplacian of v, and so we don't get a contribution from this point. Okay, that's what is written here. That's, I already mentioned it. So phi z satisfies condition 2. And if z is close to lambda n, let's say it's inside some disk, then if I look at this expansion here, then I will get only, well, I get a principal term, okay? I'm just getting aware that I did something wrong here. Excuse me. But so essentially we get the principal term, and all the other terms, they sum up, well, they are neglectable, or they sum up to this constant. So, and this first term also, it's like a constant. Okay, this comes from this z squared. So the function phi essentially behaves like this logarithm to the squared plus kn. And kn is a constant which depends on n, but not on z, if I'm in this neighborhood. And so we have the third condition. So we generate a pole, e to the minus phi will generate a pole in lambda n. All right. So as I said earlier, now we have to ensure the estimates on B. So in order to that our new weight phi, which is okay, phi z. Okay, it's written here, phi z. So in order to see that it's subharmonic, I have to compute the Laplacian and see if it's positive. And since in Hartmann's theorem, the Laplacian of phi appears in the denominator, it's even better if it's uniformly bounded. And now this is a consequence of the density condition. And everything is written here. So now we compute the Laplacian of phi, which for convenience I define in this way. Of course, Laplacian should be maybe 4 times this expression, but this is just a normalization issue, which doesn't play a role here. Okay, and then if I compute the Laplacian of phi, so the Laplacian of this is just 1. This is x squared plus y squared. Okay, this I compute the dd bar of this. Z bar mod z squared is z times z bar. So dd bar of this is 1 times 1, which is 1. Okay, this comes from z squared. And then I have to compute the d bar of this expression. The d bar of this expression will give you some positive constant and Dirac mass in lambda k. It's lambda n, in fact. Okay, and this is lambda n. Okay. And this is a positive measure, so you don't need to care about it. And it's the -1 comes from this expression, okay? And you have, of course, the coefficient 1 over r squared. And so this is bound from below by, I still have the 1 here, and minus the sum over 1s divided by r squared. But the sum of the 1s, well, I do it in this disk, and I know this is bounded by NZR. And NZR is bounded by QR squared, so that this expression is bounded by Q, and so everything is bounded from below by 1 minus Q, which is a strictly bigger constant than 0. Okay, so outside the union of the dn prime, we have, of course, that this is equal to 1, because you only have these z squared. And so this Laplacian is uniformly bounded from below, and now we can use the result by Hartmann. The W, it was integrable against the weight, and this doesn't harm the estimates. So I get U, which is in the right space. Okay, and this is it. Okay. So with the Debar method, you are able to find an interpolating function, and the idea is you start from a smooth interpolating function, and then you have to correct the smooth interpolating function, and for this you have to solve a Debar problem. So it's a partial differential equation. And to do that, well, you have to introduce a new subharmonic weight which behaves more or less like the initial one, but close to the points it has to have a singularity. And it plays some role that this is only close to the lambda case. And if you are in the annulus, then you don't feel anymore this singularity, and so everything works correctly. Okay, so this is just a small observation. So I haven't really spoken about sampling. I just gave you the result by Seib and Waldstein in this situation. Yesterday, Martin mentioned the Feistinger conjecture, which is now theorem. So I recall this sampling condition. And the right part of this implies that we have some Carlson embedding, and well, in fact, it's like the Bessel property. So necessarily we can deduce that the reproducing kernels have to be a finite union of three sequences. So in a sense, one could expect that the left-hand side is more or less for free once you can establish more or less that you have some completeness property. Okay, this is maybe not so direct. Okay, but at least we can say that none of these sequences that you get from the Feistinger conjecture can be real spaces, because such things do not exist in the Fock space due to this result which I cite here. Okay, so we're on page 14 of this presentation, and there are still 15 pages left, which I, of course, will not explain in 1 minute. But let me just mention that, so for the moment, we have considered, at least for interpolation problems, and interpolation problems, they get complete if you are in the right space, or if you stick to the right space. These interpolation problems, you can, in fact, consider much more general problems. And I just want to give you some feeling of this more general situation. And while I say here that the Hardy space situation is more or less the mother of general interpolation, of course, I mean, interpolating derivatives, this idea is older. And for example, also if you make spline interpolation, then you interpolate derivatives. But in the Hardy space, you have a setting where this is quite natural and generalizes in a more or less easy way. So the idea is that you start from an inner function, and then you write it as a product of other inner functions, and then you can look for this interpolation problem. So, okay, I define the trace this way, which seems to be reasonable. We had already always summed little L2 of the values. So here we do it this norm. We want to get f minus fn, which is in theta n h2. So maybe in this generality, it's not so clear what I mean by this. But if you take, for example, the easiest inner function, which is a simple Blaschke factor, which vanishes in lambda n, then this condition says exactly that f and fn have the same values in lambda n. And so, in fact, this yields classical interpolation. This notion was introduced in the Leningrad school in the 70s by these people. I want just mention this more general interpolation problem. So now if you take, instead of a simple Blaschke factor, you take powers of these, then the interpolation means that f and fn, they have the same Taylor expansion until a certain order, the order being given by the kn minus 1, in fact. And so you get Hermite type interpolation. And sometimes this is also called multiple interpolation. And you can consider more general situations, which I will not discuss. But what is very nice that there is a very nice characterization of the interpolating sequences in this sense. So I don't want to go into details of this. And I just want to mention, and this is maybe the last thing, that this multiple interpolation has been considered in many other spaces, like the Hardy space, of course, but also the Fock space, the Bergman space. There was also some questions about unbounded multiplicities, and so quite recently we were able to give some partial answers to the question of unbounded multiplicities in the Fock space. There are other developments. You can also consider random interpolation, for which there have been recent and less recent results, but of course the time is not unextendable, and I should better stop here. I see Javad appearing, looking at me with a very serious look. So I stop here, and I thank you very much for your attention.
Thank you, Andreas, indeed. Let's thank Andreas. Yeah, a few more minutes for questions, if any. Or comments. You may write them in.
There's a question with the answer. Okay, we have to subtract the d bar to correct, to get the Cauchy-Riemann equation. So if the function is given f, then we have to
Andreas, am I correct assuming that a PDF file will be available with more details later on by you?
Maybe. So these files, I can make them available, no problem. You should explain me how we'll arrange this.
We will discuss, yes.
Okay.
So that will be available for all, detailed studying these topics if they are interested in. So let's thank Andreas again.
Thank you very much.
Thank you very much for these wonderful talks. We have 6 more minutes, and I see Demir is with us too. So
hello.
And Lyubarsky is there too. Yura